Okay, chemistry students, I want to go over a type of problem that has multiple steps to it. Oh dear, hang on. I touched the screen and it expanded everything. Okay, let's see if I can type. So it is limiting reactant. So that's a term where you're kind of like, what on earth does that mean? So let's actually just do it in terms of generic stuff. And if there's time, I'll be able to do like a real example. So let's just do a simple problem. A plus B goes to C plus D. So your reactants are A and B, and your products are C and D. And this is what I was going to try to do. I was going to change the color. Let's see if it will allow me. So what would you actually be given? You'll be given grams of A. I'm writing it underneath too. You'd be given grams of B, and then you would be given produced. So producing, and we're just going to focus on C. You could do it for the other product, D, but we're going to focus on C. So producing grams of C, and I'm just going to make a note, this would be the actual yield. This would be, like I said, the actual yield. We can't actually do this with A, B, and C because I'd have to come up with fake molar mass values for them. So you'd be given A, you'd be given B, given some amount of product produced, C, and then you're going to be asked several questions, okay? So this is where I'm going to try to expand my color here. So your questions are going to be, who is the limiting reactant? Limiting reactant. So our choices are either A or B. And what is the theoretical yield? Theoretical yield. So in other words, no error, everything works out. What is the theoretical yield? And then oftentimes you're also asked percent yield. Okay? So the unit for percent yield is going to be in percent. The unit for theoretical yield, you're looking for something in grams. In limiting reactant, it's going to be either A or B. Reactant A or reactant B. So blue is what you're given, red is what you're asked for, and we're going to go through sort of the step-by-step process. I'm going to go back to black. So how on earth do you solve this? Okay? We're going to scroll a little bit. So number one is the limiting reactant. So we're going to do one. And there's actually sort of two parts to this. So who limits forming product C? Why am I focusing on product C? Because the question would ask you, whatever product C is, it would say, what is the limiting reactant in the formation of C, or some real element or product compound, okay? So who limits? In other words, who's guilty? Reactant A or reactant B? So you actually do this in two parts. I'm going to make it part A. We'll focus on reactant A, and part B. The plan you would take is the grams of A that you're given, convert it to moles of A. So my arrow here is a conversion. Conversion. You're just using the molar mass to do that. And then go to moles of C. And this is also a conversion with the mole to mole relationship. So for example, if there were a 2 in front of the A and a coefficient 3 in front of the C, the conversion factor to get from moles of A to moles of C in this part 1, part A, I would have on my conversion factor on the bottom, I'd have 2 moles of A and 3 moles of C. Okay, so that would just be based off of the coefficients. If they're all 1, then it's 1 over 1. You still really should set up the full conversion. So that's still trying to figure out the limiting reactant. B is same process, except you start with the grams of B that you're given in the problem, convert it to moles of B, and convert that to moles of C. Same process. The first arrow here on the left, this is you're using the molar mass of reactant B. And the second arrow, you're using the mole-to-mole relationship from the balanced chemical reaction at the top of the screen, okay? From here, what you do is you're going to have a number and a number. And one of those numbers is going to be bigger and one of them is going to be smaller. So let's just pick on A. Smaller number equals limiting. Okay? Because A, let's just say A produced 0.6 moles of C and B produced 0.8 moles of C. Well, because 0.6 is smaller than 0.8, then reactant A is the culprit. So limiting reactant is our A. He is the culprit. So that would be the answer. Reactant A. Okay. So number 2, part 2, if we scroll back up, we need the theoretical yield. You must have part 1, in this case A, correct in order to solve for number 2. So I'll make a note here. Theoretical yield. The reason we call it theoretical is because in labs sometimes there's a little bit of error transferring stuff, and if you're given, say, 5 grams of A and it's supposed to produce 0.6 moles of C, you might not quite get exactly 0.6. It might be 0.599999. So theoretical yield, what is the actual, what am I supposed to get in the end? We don't measure moles on a balance, we measure mass on a balance. So we take this same number way to down here, that same, actually I'll extend my arrow, moles of C from the limiting reactant. We actually don't care about B anymore. We don't care about the moles of C produced from B anymore. Okay, so moles of C, and I'll put a little note, from limiting, limit react. We'll just do that. Okay, so make sure that's the correct moles of C. And you just convert it into grams of C using the molar mass of C. That answer there will be the theoretical yield should there be 0 error in the experiment. So that's it, theoretical yield. Part 1 is the hardest part, okay? Once you know the limiting reactant, you can get the theoretical yield. Part 3 was percent yield. And percent yield has a formula that you must know. So percent yield equals actual yield divided by theoretical yield times 100%. And pretty much in all of life, the actual yield is going to be a smaller number than the theoretical yield. So you're going to have a decimal and then you multiply by 100%. Okay, so since I don't have any numbers to give you, the actual yield would be given in the problem. It would have to be given. If we scroll all the way back up, that would be this blue that I wrote in blue way up there. Okay, the actual amount. So they tell you this A was reacted with B, producing 10 grams of C. So then 10 grams of C is what goes on the numerator in part 3 here. Theoretical yield is the answer to part 2. So this answer here goes down there and then times 100%. That'll give you your percent yield. Let's see if we have time to do an actual problem, a real problem. And we're not going to do percent yield. We're just going to do parts 1 and 2. Okay, so let's just say we have 2NO. I'm not going to write what these are. They're all gases. Plus 5H2 produces 2NH3, which is common ammonia, plus 2 water. Okay, so we'll just do a little squiggly here. So starting with 86.3 grams of NO, and I'm just writing it underneath the appropriate substance. NO would be like our substance A. And starting with 25.6 grams of H2, find the theoretical yield of ammonia. That's the NH3. So question mark grams yielded, or theoretical yield. That's my question mark. I'm writing it underneath the appropriate substances because it makes it clear what all of the numbers apply to. To be real, I should put my unit and what my unit applies to. So NH3, we'll squeeze it in there. So the part 1, who's the culprit? Who's guilty of limiting the formation of ammonia? 86.3 grams of NO. Okay, and just so you know, NO Molar mass is 30.01 grams of NO to 1 mole NO. And then the balanced reaction is 2 to 2, so I am going to write 2 moles NO to 2 moles of NH3. Now we know that that cancels out, so technically I wouldn't have to do that part, but that's going to give me 2.88 moles of ammonia. Okay. Now let's do it with the other reactant, 25.6 grams of H2. Okay, converted to moles, 2.02 grams of H2, 1 mole of H2. That's the molar mass of H2, determined from the periodic table. And then I'm looking at this 5 here and this 2 here for the next conversion. So if you want to start with the units, moles of H2 to moles of the ammonia product C. And the 2, oops, not 2, excuse me, 5 from the balanced reaction and 2 up top. Okay, so that would give me 5.07 moles of NH3. So 5.07 is bigger than the 2.88, so the culprit, the least amount of product produced, least product, is from the NO, okay? It's from the NO. So then to get my yield, I take that 2.88 moles of NH3 and I simply do one more step to using the molar mass to convert to the grams produced, 17.03 grams to 1 mole, and that should give me, stick with my 3 sig figs, 49.0 grams of NH3. So that's how much should be produced. That's the best you can do, even though there will be extra H2 left over. The most you could make is 49 grams of the NH3, and that would be the theoretical yield. So hopefully that helps with limiting reactant type problems and calculating theoretical yield. And then from here, if you were given amount of NH3 produced, you could calculate percent yield. So thank you.